This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome to Climate Change Explained, What's Actually Happening. I'm kicking off Chapter 1 with the absolute basics because before we dive into all the dramatic headlines, we need to understand how our planet's heating system actually works. Today, we're breaking down the greenhouse effect in simple terms, so you'll finally get what everyone's talking about when they mention trapped heat and rising temperatures. Let's get into it. Right now, the air around you holds more heat-trapping gas than at any time in human history. You can't see it, you can't feel it directly, yet it's quietly nudging storms, seasons, and sea levels. In this episode, we'll unpack how this invisible system actually works. Earth's climate isn't just getting warmer, it's shifting the rules of the whole game. What feels like just weather day to day is really the surface of a huge, connected system powered by sunlight, shaped by oceans and ice, and tweaked by the gases in our air. Climate science is about decoding that system, how energy flows in, how it moves around, and how it leaves. In this episode, we'll zoom out from individual disasters and look at the baselines underneath them. How much extra energy Earth is storing, where that energy goes, and why small changes in averages lead to big changes in extremes. We'll connect rising greenhouse gas levels to measurable signals, warming oceans, shifting rainfall, melting ice, not as isolated headlines, but as a single, traceable pattern. By the end, you'll see climate change less as a vague threat and more as a set of numbers that tell a clear story. To really see what's changing, we have to start with the normal that existed before we began reshaping the air. Scientists reconstruct that baseline using ice cores, tree rings, ocean sediments, and old ship logs, building a kind of long-term climate sheet music that shows how temperature, carbon, and oceans have moved together over thousands of years. Against that backdrop, today's rapid spike in greenhouse gases and global temperature stands out as sharply as a sudden key change in the middle of a familiar song, distinct, measurable, and far faster than past natural shifts. Climate scientists often start with a simple balance sheet: energy in, energy out. Sunlight arrives mostly as visible light. Earth sends energy back to space as infrared. When these flows match, long-term temperature stays steady. When they don't, we get an energy imbalance, a small extra trickle of heat staying in the system, year after year. We can actually measure that imbalance. Satellites watch how much radiation enters and leaves. Ocean instruments track how fast waters are warming at different depths. Put the lines together and you see a consistent surplus, more energy arriving than leaving. Over 90% of that surplus is showing up as extra heat in the oceans. Only a small slice goes into warming the air or land or melting ice. So when surface temperature rises only a degree or so, that's the tip of a much larger energy shift. Where does the extra carbon fit in? The carbon cycle shuttles carbon among air, water, life, and rocks. Volcanic eruptions, plant growth, ocean uptake, and weathering all move carbon around on timescales from seasons to millions of years. Human industry and land use have added a new, very fast stream. Billions of tons of fossil carbon moved from rock to air each year. This pushes atmospheric CO2 well outside the recent natural range, and the rest of the system struggles to keep up. The numbers show that struggle. Roughly half of our CO2 emissions stay in the atmosphere. The other half is taken up by land ecosystems and oceans, which slows the buildup but brings side effects. Extra carbon in the surface ocean reacts with seawater, changing its chemistry and making it harder for corals and shell-forming organisms to build their skeletons. On land, plants often grow faster with more CO2, but that boost is limited by nutrients, water, and heat stress. Other greenhouse gases add their own signatures. Methane leaks from fossil fuel infrastructure, agriculture, and waste. It doesn't last as long as CO2, but while it's in the air, it exerts a strong warming influence. Nitrous oxide from fertilizers and industry persists for more than a century. Each gas has its own lifetime and potency, so scientists track them in CO2 equivalent terms to see their combined effect. All of this lets us connect cause and effect. Rising greenhouse gases create an energy imbalance. The imbalance accumulates mostly in the oceans. The stored heat and altered chemistry feed back into weather patterns, ice loss, and ecosystems. Different lines of evidence, satellites, thermometers, ocean buoys, chemical fingerprints in the air, converge on the same conclusion. The recent changes are large, rapid, and tightly linked to human activity. Your challenge this week: pick one climate signal that interests you: ocean heat, sea level, Arctic sea ice, or atmospheric CO2. Go to a primary data source, like NOAA, NASA, or the Mauna Loa CO2 record, download or view the raw graph, and write down 3 things: what time period it covers, how fast the trend is changing, and whether there are any pauses or jumps. Then, try to explain that one graph in your own words to someone else, without using the phrase climate change. Focus only on what the numbers and lines are doing. Think of 2 kinds of thermometers for the planet. One on fast forward, one in slow motion. Weather stations, satellites, and buoys capture the fast forward part, daily to yearly swings. But tree rings, cave formations, and ancient coral reefs hold the slow motion record. How patterns stack up over decades to centuries. When scientists line these records up, they can see not just that things are changing, but how unusual the current pace is. Here's a concrete way to picture that pace. In medicine, a fever that climbs 0.1 degrees Celsius over a day is a mild concern. The same jump every few minutes is an emergency. Climate works similarly. An extra fraction of a degree added over thousands of years gives ice sheets and ecosystems time to adjust. The same change crammed into a century means shorelines, crops, and water systems are constantly playing catch-up. We also watch where new normals emerge. Cities redesigning flood maps, farmers shifting planting dates, utilities sizing grids for hotter peaks. These real-world tweaks are traces of the underlying numbers crossing thresholds, one after another. Cities, farms, and power grids now function like tightrope walkers on a line that's slowly being shaken. As averages drift, what once counted as extreme becomes routine background noise, and systems designed for yesterday's range of conditions misfire more often. Blackouts, crop failures, transit shutdowns. Policy, insurance, and even real estate values start to encode these shifts, quietly redrawing which places and livelihoods feel secure and which feel temporary. Climate science is less a verdict than an ongoing investigation. Each new dataset is like another instrument joining an orchestra, revealing harmonies and discord in how our planet behaves. As records lengthen, we're not just confirming warming, we're mapping which choices bend the future curve and which lock in louder, harsher movements for decades to come. Before next week, ask yourself: 1. Looking at my daily life, home energy use, food, and transport, which 1 to 2 activities most clearly connect to the greenhouse effect I just learned about? Burning fossil fuels for electricity, driving, or eating high-carbon foods like beef? And what's 1 concrete swap I'm realistically willing to test for 7 days? 2. When I hear that just a 1.5 to 2 degrees Celsius average temperature rise can drive more extreme heat waves, floods, and wildfires, which local risk, for example, hotter summers, heavier rain, wildfire smoke, feels most real for my community? And how might that change my choices about where I live, how I travel, or how I cool or heat my home? 3. If I had to explain the basics of the carbon cycle and why CO2 builds up, slow natural removal versus rapid human emissions, to a curious 12-year-old tonight, what simple example or metaphor would I use? And what part of my explanation still feels fuzzy enough that I want to look it up again today? This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!